Okie dokie. Here we go. Let's go. So you'll notice that's the same name as the worksheet because that's exactly what we're going to do. We did that. That was the red and blue problem on page 1. We did that. That's the orange and green problem on page 2. We're going to go back and talk about this idea because this is what I was referring to earlier. I'm going to give you a technique to use that's going to seem silly early on when the problems are easy like the ones we've already done. And you're going to wonder, why am I doing this? Until the problems get really ugly, and then you're going to want to use that method to solve it. We've talked already about how the integral can be used as an accumulator. It adds things up. So we're going to use it to add things up to make these problems easier. This whole chapter involves taking ideas and building on it. So we're starting by finding the area of regions. Okay, so let's think about that gray area that you did on page 1. We're going to find the area first. Then we're going to find the area a different way. That's tomorrow. And then we're going to start doing all kinds of weird things, like take that area and spin it around the x-axis. So just think for a second. This will be a good mental exercise. Picture in your mind what that gray area looked like on page 1. If you want to look at your worksheet again, you can. But now imagine what the shape would look like if you took that region and spun it around the x-axis. What would that three-dimensional object look like? Or take that same region and spin it around the y-axis. What would that thing look like? We're going to be calculating all kinds of different things with those, mainly the volume of those figures. And doing all kinds of weird things like punching holes through them and doing all that other stuff. But that's a long way away. We've got to get this under control first. And then, of course, you should be able to make great scrambled eggs. Who adds milk to their scrambled eggs? Anybody add water? Anybody do a combination of the two? Anybody do heavy whipping cream? Or half and half? I'm telling you, you want to elevate your scrambled eggs to a new level, add some heavy whipping creams. You're in for a treat. It's your cooking tip of the day. Okay, so we did this, we did that. We're going to skip all this because we've done it already. Okay, that's okay. Yeah, I did that. Great. Okay. Wait, I'm looking for the example here. But okay, this is important. In all of those parts that we did, the red and blue problem, the green and orange problem, we always did the top function minus the bottom function. That idea stays true for all of these problems. Top minus bottom. It's one of those buzz phrases that you're going to be repeating to yourself in your head over and over again when you're doing these kind of problems. Top minus bottom. If you're given a picture, it's pretty easy. You will encounter some problems where you've got to figure out which function is on top. We'll cross that bridge when we get to it. Okay, but top minus bottom. Just to make sure you've got this under control, let's take a look at another example. But now I'm going to introduce this accumulator idea. So we're going to break these area problems down into something very simple, and that is the area of a rectangle. If you can find the area of a rectangle, you can do any one of these problems. Assuming, of course, you can solve an integral, whether you FN int it or solve it by hand. So I'm introducing this concept of a representative rectangle. My representative rectangle in that picture is that black thing. And you're saying to yourself, that's not a rectangle, that's a segment. But I'm telling you, it's a rectangle. Two things I need to know for a rectangle: the height and the width. So let's start with the height. Even though it's up there, this is where the top minus bottom comes into play. The height of that rectangle is the top function minus the bottom function. Then I need the width. And we'll talk about the width in a second. But hopefully by now you understand the concept that if I want to find the area of that entire region, if I can find the area of one rectangle and then add up all those rectangles, I would have the area of the whole region. So question number 1, how many rectangles do I want to represent that region? To get the exact answer. I heard somebody say it. Infinite. And if the rectangles are, if there's an infinite number of rectangles, how wide would each of those rectangles be? 0. Pretty close to 0. So close to 0 we can't really measure it. So what we're going to do to represent that width is we're going to use the differentials that we've been talking about already. So the width of this rectangle is dx. Infinitely small. Are you with me? Okay, good. So if you can do that, solving this problem is not difficult at all. So I need a representative rectangle. Where am I going to put it? It doesn't matter. This one happens to be in here. So there it is. It's green. I just stuck it somewhere in that little leaf-shaped cat's eye looking thing that we're going to find in the area of. I do want to say on a side note, though, notice the terminology, a region bounded by the graphs. There's a lot of regions with these two graphs intersecting, if you imagine going on forever. When it says bounded by, though, we're looking for a finite area. Okay, so how tall is that rectangle? No.
No.
Because remember, I can put that rectangle anywhere, so it's not going to be a numerical answer, it's going to be a equation or function answer.
X minus x squared.
Say again.
X minus x squared.
Square root of x minus x squared. Now, how do you get that? We go back to the same thing I did a couple slides ago. What function is on top, red or blue? Seems like a silly question, but I'll ask it anyways. Red. So we're doing red minus blue. The red function is the square root of x. So we get the square root of x minus x squared. We good? How wide is that rectangle?
0.
No?
Very close.
Well, very close to 0, which we represent using dx. Okay. So there's the area of the rectangle. Top minus bottom times the width. And that width, again, is represented with dx. In essence, it's 0, but that wouldn't make any sense. We'd get 0 as an answer. Again, this is the hard part. The rest is easy. Now I just need an integral, because I'm going to add up all those green rectangles. So it's an infinite number of green rectangles. And I'm going to add up rectangles from where to where. In other words, what are my limits of integration? 0 to 1. Sometimes you'll be given this point like I did here. Obviously, you should know that's the origin. But this point at 1, 1, depending on the problem, they'll tell you where the functions intersect, or you may have to solve for it. You can solve for it, set the two functions equal to each other, and solve. So plugging in our numbers, we get that, and therefore we get that integral. We're adding up rectangles from 0 to 1 of top minus bottom times the width, which is dx. At this stage, I don't care about the answer. That's an integral you should be able to grind out at this point in time, or you can fn int it. That's not what we're spending the time on. We're spending the time on being able to put together these integrals. Don't get sloppy. By that I mean there's a lot of little minutiae there that you can screw up on. Like for instance, A equals is very important because soon we're going to switch from area to volume. And you need to distinguish that you know what you're doing, that you know you're finding an area. And I've been very loosey-goosey about the dx on the end of that. Now it becomes crucial because that dx represents the width of the rectangle. Without that, you don't have a rectangle. Without the rectangle, you don't have an area. So you've got to be sure to include your dx. Okay. This we talked about already. What happens when the two regions, when either the top or the bottom changes? So this one's a little bit different than the one you did on the worksheet. On the worksheet, you had only two functions and they crossed over. This is three different functions. For discussion purposes, what's the equation of the red line? Is it x plus 6, x cubed, or negative 1/2 x, I mean? X plus 6. Which one's the blue one? Negative 1/2 x. And I don't have green, so we'll just pretend that you know it. I've done some of the work for you already in that I showed you that you have to split this area into two different regions. Why two different regions? Because you have different tops or bottoms. Okay, so let's set up an integral for R1 first. What integral am I going to use to solve for the area of region 1? To make your life a little bit easier, let me draw your representative rectangle in there. Okay. What's the area of that rectangle?
6 minus 1 half x. Times dx. Minus 1 half x. No? Where are you? Oh, plus 1 x. Not dx.
Good. Top function, x plus 6 is the red one, minus the bottom function, negative 1/2 x, gives you that. What are my limits of integration? I'm adding up rectangles in region 1 from what to what?
Negative 4 to 0.
Good. What's the integral for region 2? Here's your representative rectangle. Let's go backwards here. What are my limits of integration? I'm adding up rectangles from where to where? 0 to 2. What's the area of that rectangle?
X plus 6 minus x cubed dx.
Perfect. Top minus bottom times the width. It's up to you how you want to solve those. The first function, you can combine the two and do 3/2 x plus 6. You can leave it as is. It's entirely up to you. But again, that has to be split into two different integrals. This isn't the one we did, like the green and orange one we did on the worksheet where you could just double an area. These areas are completely different. Now that you have the basic concept under control, how could we make it more interesting / difficult?
Make it one.
Say again?
Make it like one region.
Okay. How? You mean do that as one region?
Yeah. Or I don't know, makes it harder.
Yeah, sure it does.
Not provide a picture.
Not provide a picture would be a good, that's a really good idea, actually. Thanks, Tom. I thought of that already. How else? No.
Split it in half horizontally.
Yeah. Okay, so what if instead of our rectangles being vertical, what if the rectangles were horizontal? That'd be fun. Thanks. Guess what we're doing tomorrow? We're doing horizontal rectangles. It's actually not that bad. There are certain situations where vertical rectangles won't work, and I'll show you what that looks like tomorrow. Some of the problems, in fact, tonight on the homework will say, do this in terms of x and do it in terms of y. We haven't talked about it in terms of y yet, so you're just going to do it in terms of x. We'll talk tomorrow about how you're going to do it in terms of y. But what I mean by do it in terms of y is that instead of having x's in your integral and a dx, you have y's and a dy. It gives you a different type of problem. I could incorporate trig. That would be fun. You love trig. Similar to the problem we had on the worksheet. After that, I'm pretty much out of ideas. There's not much else I can do to make the problem more challenging. So if you can handle the basics, you should be able to handle it when it gets really nasty also. I did all the work there, blah, 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 and we'll stop there too.